Great. All right. So hello, everyone. Thanks for being here today for our AFMS seminar. So today it's my pleasure to introduce our speaker, who is Dr. Ashleigh Hutchinson. So she's a senior lecturer at the University of the Witwatersrand in Johannesburg in the School of Computer Science and Applied Mathematics. She's also the Assistant Director of the National Research Foundation Centre of Excellence in Mathematical and Statistical Sciences. Dr. Hutchinson is interested in developing mathematical models to solve real-world problems in fluid mechanics using both theoretical work and practical applications. And she's going to be talking about some of this work today, so please take it away, Ashleigh.
Thank you so much. Before I start, I just want to thank the organisers for this opportunity. I am slightly nervous, but I'm looking forward to presenting this work, and I hope that it will be of interest. The title of my talk is Navigating Turbulent Waters, and I just want to introduce some of my collaborators. Nick Hale is a numerics expert who is from Stellenbosch University in South Africa. I would suggest that if any of you are planning on visiting South Africa, please do go see Stellenbosch. There's lots of wine, farms, and beautiful scenery. Then there's Kendall Bourne, who was a former master's student of mine, and Professor D.P. Mason, who supervised my PhD. So we've got a good group of collaborators, and we all have a variety of different skills that we have used in this work. Okay, so here's just an outline of my talk. I'm going to just provide a brief introduction to turbulence. I realize that there are many people sitting in the audience that know more than what I do, but I always think a gentle introduction is good in a talk. Then I'll just briefly look at some of the approaches to modeling turbulence. So I can just give an overview of what we have looked at and what we are still planning to look at. Then we'll zone in onto the Eddy viscosity closure model, and I'll explain why I do that a bit later on. And I'll be looking at a particular example, namely turbulent wakes, as they do have many important applications in nature and in industry. So I'll just end off with some conclusions and references for those that are interested in looking at this work further. Before we actually hope to model turbulence, we need to understand what is turbulence. Unfortunately, this is not the easiest question to answer, but what we can do is we can associate certain characteristics with these turbulent flows to provide some sort of a description. So I've listed some of these characteristics here, and we will be using these ideas later on in the talk. So we know turbulence when we see it, but it is not always easy to describe. However, what we do see is that there are random fluctuations that are time and space dependent. The motion is irregular, so it's impossible to depict any pattern. There's also a multitude of scales, which is very nicely illustrated by looking at the eddies that have different sizes. Also, what's important is that it's impossible to repeat an experiment and expect the same measurements. So because turbulent flows are random and they're also very sensitive to initial conditions, there is quite a big job ahead when it comes to modeling these flows successfully. Many researchers consider turbulence as an unsolved problem. This is a topic of some debate. However, I must be honest, I'm definitely on the side of it being unsolved. And some of the reasons are because the characteristics of turbulent flows have really been discovered through experiments and not so much the theory. So as someone from a very theoretical background, who does not have any, or I mean very little experience with experimental results, it is very interesting to note that all these observations have come from there. And therefore, it is just so important to incorporate different areas and fields of research in order to understand this problem. We are certain about the equations to some extent, the Navier-Stokes, but what's not so certain is how to actually go about solving them. Now, you could say that because computational approaches are increasing, getting better almost on a daily basis, computational approaches can be used to solve the equations. However, I would argue that computational approaches are not a substitute for understanding. So in this talk, I'm going to be looking at more simpler models, and we're going to try discern characteristics of models that do lead to good, good comparison with data. So that's what we will be looking at. Okay, so it's always interesting, I think, to see the views of others, especially famous people like Heisenberg and Feynman. Basically, turbulence is a difficult problem. I'm sure the context of these quotes might have changed over the years, but the gist is really the same. It's a difficult, fascinating problem that can either really put someone off or inspire them to try and make a contribution. There are a number of famous scientists, and I must say that this list is obviously not complete. It's just taken from a book called A Voyage Through Turbulence, which is one of my favorite books. It just provides a nice historical overview of turbulence and some of the main contributions that have come out. What I actually found the most interesting about this list is that a lot of these researchers were engineers. Now, again, someone from a very theoretical background can now actually appreciate that really it was the engineers that have probably made the greatest contributions. So it was really driven this research forward in that direction. So as we know, there are many different approaches to modeling turbulence, and a lot of these approaches were developed by the researchers shown on the previous slide. They can be grouped into different categories. We've got simulations that really involve computational methods, and then we've got turbulence models. We will see that later we need some quite hectic numerical tools to solve some of these turbulence models, but in essence, they are technically computationally less expensive. With turbulence models, the aim is to solve for the mean flow variables, so we're not interested in the actual detailed structure of the turbulent flow. We just want to solve for these time averaged quantities to get some kind of understanding and a way to model. We need a closure model to complete the system of equations. So the goal of this talk is going to be to look at different closure models, and then I'll actually show you how they compare with experimental data. We will then go on to discuss which models were successful and also why they were successful, as it might also help down the line when developing new closure models. We start simple. We're going to look at eddy viscosity closure models. And basically in these models, we take the flow, we divide it up into a mean motion and an Edding motion. So here we've got ui, which is the ith components of the velocity, is just equal to its mean plus the fluctuation. So we substitute these variables into the Navier-Stokes and then we average over them. We'll be looking at statistically stationary turbulent flows, which means that the average of the fluctuations is 0. Provided that our time interval that we are averaging over is sufficiently large. When we do this process, we get a whole lot of terms disappearing, but the averages of products of the fluctuations are non-zero. So what happens is that we get these additional terms coming up in our equation, and these are not known. This is why we need a closure model to complete the system. So I've written the Rand's equations in this form over here, just so that we can identify the different stresses and then also look at the closure models for the turbulent stresses. So we see the three types of stresses. We've got the isotropic, which arises from the pressure, the viscous stresses, which are there for all fluids that have viscosity, and we've also got the turbulent stresses. With these eddy viscosity closure models, one way is, well, to look at this is to take these turbulent stresses, sorry, I keep losing my cursor, to take these turbulent stresses and to express them in the same way as the viscous stresses. But instead of being related by the constant dynamic viscosity mu, we introduce a turbulence viscosity mu t. unlike the mu, which is a constant, this mu t can depend on space and velocities, gradients, and a whole lot of things. So we'll be looking at different forms for that, and then we'll be comparing it later. So this is basically what eddy viscosity models do, and they're quite simple in the sense that turbulence is really modeled as an apparent increase in the viscosity of the fluid. It's always convenient just to separate the flow into what we know about laminar flows and how turbulent flows change the structure. So we define an effective viscosity, which is just simply the sum of the kinematic and the turbulent viscosity. So for laminar flows, this term would not be present. So we can just always compare back just by knowing that. What's really great about eddy viscosity closure models is that they provide a simple description of turbulence, which seems to be pretty intuitive. They're relatively easy to implement. I will argue that point later, as the one model gave us many sleepless nights and migraines. They often agree well with experimental results, which is perhaps somewhat surprising. And in some cases, exact solutions can be found. Exact solutions are fantastic because they are free from numerical error, but they also provide a baseline to compare other models to, and it also helps to develop some numerical schemes. Okay, so we'll be looking at my favorite example, which is turbulent wakes. And I really enjoy studying turbulent wakes because they have so many important applications. As you can see in this picture of a wind farm, you can see that turbulent wakes develop behind these turbines. Now, I've recently just learned a bit about wake steering control operations. And basically the goal is to optimize the generation of energy. Turbines that are situated in wakes of turbines in front of them have decreased power production. So wake steering controls are very important, and a good understanding of these turbulent wakes is required so that you can actually effectively run these wind farms. Now, this is clean energy and renewable, which is great, but on the other hand, there are certain bird species, such as the bearded vulture, that actually use the lift from the wind turbines, and often they end up hitting the turbine behind it. So of course, with everything, there is massive positives, but there are often downsides as well. So understanding turbulent wakes for nature and for humanity is actually very important. I won't go into the description of how we get to the equations in too much detail. I'd like to more talk about the results that we got. But just a brief description is provided. So we've got an object situated here. It's stationary. We've got a laminar mainstream flow with velocity capital U in the x direction. It flows past this object and we get a wake forming behind it. We'll be looking at the far wake, and for the far wake, it's convenient to define a velocity deficit, W bar. So we write all our equations in terms of the velocity deficit. The star here just indicates dimensionless variables, but due to convenience, for convenience sake and laziness when it comes to typing, we omit that as we go along. So we get these two equations here. This is just conservation of mass. Here we've got momentum. We need to solve these subject to some boundary conditions. Two of the boundary conditions arise from mainstream matching. So as we move off into the y direction, the turbulent wake must merge with the mainstream flow. So this means that the velocity deficit must vanish, and also its first derivative, so that its vorticity is 0. The boundary of the wake is denoted by ybx, which might be surprising for some. You may ask, why not plus or minus infinity? In some of the closure models that we look at, a finite wake boundary actually comes out. We argue that this is non-physical. It should be extending to infinity and not have that singularity present. However, for example, Prandtl's mixing length model, we get a finite wake boundary. So we just denote it by ybx. It's being understood that this actually is infinity for some of the models. We've also got some conditions on the axis of the wake. The velocity deficit is a maximum, And because of symmetry, the y component of the velocity also vanishes. Now, all of these equations are homogeneous, and so are the boundary conditions. So we actually get an additional constant coming out that we need to solve using a conserved quantity, which is shown here. Okay, so I guess now for the quite exciting bit, because it's not the oldest work either, it's still fresh, and we haven't quite gotten sick of it just yet. Maybe in a few more days that will happen. We wanted to look at a whole suite of models and compare them to experimental data, and none of us have any experience with this, but luckily there is this really amazing paper where they have conducted very detailed experiments. Unfortunately, the data has been actually lost, you know, as the ages have gone by. We contacted the corresponding author who gave us permission to reproduce the results as much as we could. So what we did look at first is comparing our models to the best fit curve that was found in this paper. The best fit curve, that term should be used with caution, because we will argue that perhaps it's not the best fit. But anyway, what happens is that in this profile here, this is a mean velocity profile, these different shapes correspond to different wake generators. So you can get airfoils, cylinders, for example, flat plates, but they all have this universal property that their mean velocity profiles look the same if you're considering the far wake. So all of these collapse to this function that is given here, and this function and the data were normalized so that it satisfies these two conditions. So when we solve our models, we need to then do a rescaling of our variables so that we can match up to these conditions in order to allow for direct comparison. Now, even though the data has been lost, there are always ways, and in particular, programs such as Python and MATLAB are very good at finding those ways. So here, I'll just show some of the data that was extracted. The extracted data that we looked at, we were sure to only extract data that we were sure about. So you can see that closer towards the boundary of the wake, the data does become more noisy, and we do understand that that will limit us in what we can actually say about these models later on. But we did extract a whole lot of data points, ones that were very clear. But first, we're just going to look at the best fit curve on the previous slide. And it is important to mention that that curve was not determined from any closure model. That is just a fitting tool. But we'll first compare the models to that, just to gain some insights. And then later, I'll show you the comparison with the actual data. Okay, so of course, why not start off with the most basic model, the easiest one, and that's the constant eddy viscosity model. So we've got our governing equations shown here. We can solve this by introducing some similarity variables. We substitute into the equations, solve subject to the boundary conditions and the conserved quantity, and then we rescale the variables to get the normalized profile so that we can compare this directly. So when we do this, this is what we get. And I just want to make a number of comments because it always helps to understand where models have been successful and where they have also gone wrong. So with the constant eddy viscosity closure model, you can see the plot over here. The solid line is our model and the dotted is that best fit curve. This is a very simple model that has an exact solution, so that's definitely a positive. What's also interesting is that it matches the data very well, except near towards the edges. So the reason that is given here is a reason that was not it was not seen immediately. I'm not, perhaps we should have. But the whole thing with the constant eddy viscosity models, that because your eddy viscosity is constant, as you tend to infinity in the y direction, that eddy viscosity obviously won't change, it being constant. But now, because the turbulent wake should merge with the mainstream laminar flow, the eddy viscosity in a model should really actually be vanishing at the boundary of the wakes. So that was something that we suggested was a possible issue when it came to looking at this. All right, so let's move on to some slightly more complicated models. I'm not sure if everyone is familiar with Prandtl's mixing length model, but I must be honest, the derivation of this model has bugged me for about a year. So I'm going to present it here because we'll also need it later on when we look at another model that does not have a derivation currently in the literature, from what we can see. Okay, so for Prandtl's mixing length model, the aim was basically to improve on the constant eddy viscosity model. It's interesting that we'll see later, it's not so much of an improvement, in my opinion, but nevertheless, let's look at how it works. So with Prandtl's mixing length model, the whole idea is based on the fact that turbulence, turbulent particles, they coalesce, they form lumps. These lumps move as a whole, retaining their momentum until they mix in with the surrounding fluid. So that's really the whole picture that we're looking at. To provide a very simple derivation, it's best to look at parallel flow. So we have the mean velocity u bar and the fluctuations u prime and v prime. So what we do is we zone in onto one such particular lump that's positioned at y, and we look at how this lump is transported into the next layer. It could be up or down. This L prime can be negative or positive. So it's the turbulent fluctuations that displace this fluid lump. Now, the greater the fluctuations, the further this is going to be displaced. So we look at this fluid lump moving from one position to another, and we use that to gain some kind of estimation for the sizes of the fluctuations. So for a fluid lump moving, let's just look at the top half for now. In this direction, we must have that v prime, which is the y component of the fluctuation, must be positive in order for this to happen. And from conservation of mass, this in general means that the u prime, which is the x component, must be negative. So L prime here is a random variable that is space and time dependent. And basically these fluctuations will displace these fluid lumps. After this distance, L prime, the fluid lump would mix in with the surrounding fluid. But during this transition, the velocity of the fluid lump is retained. So to measure the strength of the fluctuation, we look at the velocity, the mean velocity in the new layer, which the fluid lump has just entered, and we take off its velocity. So that's how we measure the strength of the fluctuations. We then use a Taylor series and just really hope that L prime is small so that we can neglect terms of order L prime squared. Something quite common that we do in applied maths. But hopefully it will be okay. I mean, it should be okay. It's not a complete disaster, as we'll see later on. So basically what we do is we set u prime equal to minus delta u because it's negative. We'll just consider positive L prime for now, then we later relax the condition, just for illustration. So using this idea, we can write our velocities. Just lost my mouse again. Okay, so we can write our velocity in the x direction as u bar plus u prime. The u prime here is just minus L prime du bar by dy. And then for the v prime components, all we do is we say that it's related to the u prime by some constant c, and it will have opposite sign. So that basically just takes care of the velocity components for Prandtl's mixing length model. So what we do is we take the expressions for u prime and v prime that we just found, and we substitute it into this equation here, and we get this expression. So you can see that the average of L prime is just really the variance. And we'll take c times that to be some other function L, which is referred to as the mixing length, from which this model derives its name. So with the eddy viscosity closure models for parallel flows, we only have the one derivative coming out. So when we write the stresses in terms of our eddy viscosity model, we can compare these two expressions and just get the turbulent viscosity, which then is written in terms of the mixing length and the absolute value of this derivative. The absolute value is included because we might be looking at du bar by dy positive or negative. So that's just to take into account both of those cases. Now, what's really nice about this model is that it can be easily transferred to apply to wakes. Because we're using the boundary layer approximation for our wake flows, all we need to do is just to replace this derivative with the partial of the velocity deficit, because in the stress terms, it's the same form basically for the wakes as what it is for parallel flows. So finally, we get an effective viscosity that looks like this. This is just dimensionless. The first term corresponds to the dimensionless kinematic viscosity. The second is then the turbulent viscosity. So this is what we have. This is the first model that we the second model that we look at. Now, of course, like with every model, there are a number of issues with it, and I'll just explain some of those so I can motivate as to why we looked at the next model. So Prandtl assumed that the kinematic viscosity is small compared to the turbulent viscosity, and he neglected it. This assumption is actually not true on the axis of the wake and at the boundaries, and that's because of the boundary conditions and the fact that the first derivative vanishes at those points. So that was definitely one issue. There was a solution that Prandtl himself looked at, and we call that the extended mixing length, Prandtl mixing length model. We still get the issue at the boundary though, in that the turbulent viscosity is much smaller, which we actually want that to happen. We want it to tend to zero so that it can match with the laminar mainstream flow, but then it's incorrect to say that it's, that the kinematic viscosity is negligible. Also, a huge problem is that the extended Prandtl model, although it does improve on many issues, it introduces two mixing lengths now, and these mixing lengths remain unknown. The same issue is also found in Prandtl's mixing length model. You can't obtain the mixing length. You need to impose an additional hypothesis, which is what Prandtl did, and also a finite wake boundary is predicted. Both of these issues can be rectified by including the kinematic viscosity, which was work that was conducted during my PhD. So these are actually all resolved just from the very simple inclusion of the kinematic viscosity, which is quite amazing. Unfortunately, though, there isn't enough time for me to go through those details, so you'll have to take my word for it. But let's just look at how Prandtl's mixing length model compares to our best fit curve. So as you can see, the results were slightly disappointing. We expected perhaps that this would fit a little bit better than the constant eddy viscosity, but it's not really good. So you can see that it underestimates the data near towards the center, but it overestimates it later on towards the boundaries. So it's really not a desirable fit at all, which prompted us then to look at the extended mixing length model. Now, unfortunately, with the extended mixing length model, there isn't a huge amount of literature on it. So I'll just explain a bit. There are papers that consider simplified versions of this mixing length model that also do have derivations, but the actual full-on extended mixing length model, as proposed by Prandtl, that appears to be lacking a detailed derivation. And one of the things that we wanted to do was to rectify that. It was kind of just stated without any proof, and we know that Prandtl had fantastic insights. A lot of his papers we actually had to translate from German, so it was a good thing that my former master student actually speaks some German. But we could not find anything that really just described this in detail and where the second mixing length comes from. So we attempted to do our own derivation, and I'll briefly go through it. The whole goal of the extended model is to improve on this approximation, and in particular, an improvement on this term here is really what's going to be made. Now, with turbulent flows, we know that we cannot repeat an experiment and expect the exact same measurements. So why not consider 2 experiments where the turbulence fluctuations will differ for each experiment, and we can denote that by assigning an L1 prime to the first experiment and an L2 prime to the second experiment. So strictly L1 prime and L2 prime will actually be sets of values because it's a random variable. So you'd have to look at a whole lot of measurements for that. But we're just denoting the 2 experiments by those different quantities there. So what we do is we look at the derivative of the average because we want to improve on this over here. And we notice in this case that all the derivatives, the mean derivatives, are equal to the derivative of the mean. So we can take this expression and write it as the product of the derivative of u1 bar and u2 bar. Now, because these are 2 independent random variables, they correspond to 2 different experiments as they have to be independent. The product of the averages is the average of the products. So this step over here just expresses the fact that they are random variables. So we take these 2 expressions and we average over the entire thing, and actually, lo and behold, we get out the extended mixing length model. So that was quite a nice surprise. It was something that we looked at that was, we hoped to think quite creative, but what was very nice is that we actually get the extended model coming out. So with the extended model, we get the eddy viscosity in the following form. This is still for parallel flows, which we can still extend to wakes. There's no issues there. Look, I should mention that over here, there are a couple of assumptions involved. We have to still assume that the boundary layer approximation still applies. I know that turbulent fluctuations can be quite large in other directions, but anyway, let's just pretend all is good, like we often do. So with the effect of viscosity, we non-dimensionalize as well. And again, we just get the sum of the kinematic viscosity and the turbulent viscosity. Just to make things look a little bit better, we define beta to be this term over here and alpha to be this term. So instead of worrying about all these quantities separately, we play around with beta and alpha. So as with the work in my PhD for Prandtl's mixing length model, 2 cases were looked at, one where the kinematic viscosity was included and then when it was neglected. And we found that there were significant advantages to including it. So what we do is we include it as well in the extended model to see what also happens. What's really nice about this model is that you can actually get back to the original Prandtl model if you had to set L2 equal to 0. I'm hoping that some spark of inspiration will come about as to how that actually relates physically to the problem that we're looking at, but I will try not to venture off on a tangent for now. Okay, so the equation that we looked at, it is actually rather complicated and the scaling solutions are not as straightforward, but of course things always look easier once you've done them. So I will just briefly mention what we looked at. So we had our similarity variables, which were the same as for the constant eddy viscosity. That is expected because we want to be able to compare them as well. When you include the kinematic viscosity, the mixing lengths come straight out of the expression, which is fantastic because if you exclude it, you don't get this result and you have to apply what's called Prandtl's hypothesis, which we showed could take on various forms. So in terms of our similarity variables, we get all of our boundary conditions and also our conserved quantity. Because the upper limit and integrand must be independent of x, we know that this must be some constant xi b. Again, for some of the models, xi b is going to be infinity, which corresponds, I guess, to the more realistic models. So we get this ODE coming out, which, as you can see, it's not the simplest of ODEs. I mean, it's got squares and square roots and all sorts of weird things happen in the numerics. What is nice though, is that we can integrate it once. And this is actually a property called the double reduction theorem, in that if you have a conserved quantity, you can actually always integrate an ODE again. So we integrate again, and we get that the arbitrary constant is 0 just by applying this condition here. Oh, okay, so I was meant to do the whole big reveal, but anyway, I guess it was on the poster. So what actually happens when we look at this extended model and we compare it to the data? Well, I will just say that we were absolutely amazed at how well the fit is. This was definitely a day where I took out a bottle of Stellenbosch wine and celebrated, because this was just fantastic. We were extremely happy with this result. The numerics was all done by Nick Hale, so it was very complicated. I know that he used Laguerre's spectral method and then did all sorts of other things. But anyway, the solution, everything appeared to work very well. So we were absolutely floored with how well this data was matched by this model. Okay, so of course we were just fitting to that base fit curve. So what actually happens when we compare to the data? I know that this graph is a little bit messy, so I do apologize, but I'll just point out a few key features. So the cyan dots correspond to the data points that we could actually extract. As you can see towards the boundary, we were unable to do that. Hoping at one stage that at some stage we'll, I don't know, be able to get involved in conducting some more experiments of that nature. Okay, so the solid line is the base fit curve. The constant eddy viscosity is the dotted purple. Notice that it's an exceptionally bad fit as we go even towards the edges. I haven't gone fully towards the end, but you can see it's already starting to cause quite a mismatch. Prandtl's mixing length is the blue one, which in my opinion doesn't fit well at all. Then the extended Prandtl, we looked at different values of the parameters. We did a sensitivity analysis, and basically as you increase the one parameter, you get closer and closer. Now, of course, perhaps plotting only the mean velocity profiles, perhaps that's actually not enough to compare. So we did look at the shear stresses. It was actually someone at the University of Melbourne, I won't put them on the spot, but when I met them at a conference a year ago, they stressed the importance of the shear stresses. So we went through all the calculations for the shear stresses. However, what was perhaps maybe slightly disappointing, or I don't know if it's of interest, is that when we got the similarity profile for the shear stresses, it did depend on the turbulence Reynolds number, but apart from that, if you scale that out, it's related to the y component of the velocity, which can just be solved in terms of the mean velocity profile f. So all the properties corresponding to f really were just transferred to g. So we couldn't deduce any new information from the shear stresses. And of course, not having the data at our disposal, it also made it more difficult in terms of that. Extracting the data comes with its own errors as well. So we just have to be careful. What we are confident about, though, is that the extended Prandtl model is definitely superior to the others. And I did not include the table here, but we looked at an error analysis and we looked at how well the extended Prandtl fits the data. And based on the data points that we were able to extract, it seemed to be about 20% better than all the other models, which is really, really, really significant. I think it's a good starting point also to look at other models to see if we can do even better. So there are a couple of things to consider. We can consider N experiments. Quite looking forward to doing this. I think that it will give really nice results. I'm hoping, but we'll see. So considering N experiments and re-looking at the extended Prandtl model derivation. And also we realized that with the closure models that generally fit the data well, we have this property that the eddy viscosity vanishes on the wake boundary. But what happens is that the solution tends asymptotically to the solution for the laminar wake, which is an exponential solution. So there are a whole range of different closure models that actually satisfy all those properties. But we don't want to just apply arbitrary functions. We want to back it up with the physics as well. So we want solid derivations. and models to look at that all tie in with the physics. We won't just look at something random. So that's really what we're looking at in the next sections. And just to conclude a bit, from each model, it was a very good exercise looking even at the simpler ones, the constant eddy viscosity, which has been compared extensively to data before, but us doing it ourselves gave us some insights into why it wasn't a good fit towards the edges. We feel that we were able to derive the extended Prandtl model, which was quite an achievement. And I think what is the icing on the cake is that the extended Prandtl model seems to be incredibly accurate. So these are the results that we have. We are still looking at further studies. We hope that it does set the stage for more work to come, and that it will be of use in other applications in engineering. So thank you. Oh, and some references. So if anyone was interested in the idea of including the kinematic viscosity and how that assists in determining the mixing length, there are a couple of references here that you can look at. Obviously, I'm very happy if anyone wants to ask any questions or send me an email. I'll be very happy to engage. Thank you very much for listening.
Cool. Hello.
Hi. There we go.
Yeah, so thank you so much for your talk. Your timing is excellent. Sorry,
really I think it was a bit early. Maybe I rushed through it, but it would be nice to, get some comments and questions.
Always better to finish a little bit early and have time for questions, I think. So thank you so much for talking to us about these really interesting
you for the invite.
Turbulent models. So we do have time for questions. If you're in the audience and want to ask a question, you can either unmute your mic and ask it, or you can raise your hand in the participant list and I can call on you. Cool. So I think we have one question already. I'm not going to be able to see. Sorry, the person with their hand up. Go ahead.
Tusha.
Sorry. Yes, go ahead. Oh,
Tusha, your microphone is mute.
Yes.
Unmute yourself, or it's something wrong with your...
Hello, can you hear me now?
Yes, perfect.
Yeah. Ashley, this is Tushar. I'm a PhD student from University of Melbourne.
Hi,
first
how
of
are
all,
you?
thank you so much. It was a very nice talk. Very concise and, with little use of words, very nicely explained. I just have a very naive question, perhaps, or I might have missed. When the extended Prandtl length model, in the mathematical side, you had an expression where it was averaging over the product of du1 by dy and du2 by dy, and you said it's equal to average of individuals. Like, I might have missed the assumptions, but mathematically that doesn't necessarily hold, right?
Yeah, so that's actually a very good question. Thank you for that. So in this case, perhaps what I should have explained a little bit better, I'm hoping that there are experimentalists here as well that can assist with this. So with these two experiments, we make them as close to identical as possible. So in that case, in the models that we look at, it's the turbulent fluctuations that are imposed on the mainstream flow. So that's really the description that's considered. So if we make two experiments as close as possible to being identical, alternatively, you could also look at one experiment in just maybe different times. But in that case, the mean flows should be quite close together in the context of the models that we're looking at. It's the fluctuations that will change from each model, from each experiment, basically. But if you try and make it as close as possible together, there shouldn't be too much, change in the mean flow based on the description of the fluctuations being imposed on them.
Okay, so it's an assumption, the way the experiment is being done. Okay.
Sorry, an assumption that perhaps I should have mentioned.
Yeah, I'm experimentalist myself, so I had the question. Thank you so much.
Oh, thank you so much. Thank you.
Well, thank you. Anyone else from the audience? So I had kind of a quick question for you, Ashleigh, which was, I didn't quite understand when you were talking about the shear stress results, you were talking about F and G, the functions, and I didn't quite get what they were. I think I probably just missed it. Sorry, you probably explained it.
No, I don't think you didn't miss it at all. I can definitely say that. So yeah, so with the shear stresses, it was, you know, drilled into my head that they are very important. So what we did is we calculated the expression for them. What we found is that for these models, they all related to the y components of the velocity. So you can actually write the shear stresses as 1 over the square root of the turbulent Reynolds number times the y components of the velocity. There's a negative as well. So from our models, that is the expression that we got. And we were hoping that with the shear stresses, it would give us more insight into the characteristics of the models that are successful. But because they just depended on the mean velocity profile F that we got, and that we were already comparing to the experimental results, it didn't actually give us any new insights into that, because it just depended on F. And it was quite a lengthy calculation that led to that result, which again, I think we all thought was maybe also a bit surprising.
Okay, yeah, thank you for explaining that. We have another question in the audience. Go ahead, P. Broadridge.
Yeah, hi Ash, Phil here.
How's it, Phil?
Thanks for that, nice and clear and very informative. I think I remember right at the start, you said the shape of the barrier doesn't matter so much. So that probably means you just have to go back far enough so the traces of most of the parameters of the barrier disappeared into the turbulent wake. But I guess the distance that you need to go back actually is partly determined by the shape of the barrier. So, you know, if you have a flat square barrier, it's going to cause a different direction of the flow for a considerable distance, or for a diamond shape or whatever. Can you predict how far back you have to go with a turbulent closure model? And actually, I guess they just use cylinders in the experiment, or something else.
So, no, thanks for that, Phil. You know, what was nice is having no experimental knowledge of this. The paper was well set out. They actually considered a whole lot of generators. Cylinders, I think the one was even a plate in this direction. And what they did is they measured how far they needed to go based on the Reynolds number, where the effect was, you know, that you get the same profile. But also it is the normalized profile. So they did do a scaling of some, you know, the variables before getting that result. So that might have also had an impact. They were quite careful because they talk about this property of it being a universal profile. They do indicate how far down you need to go. It was defined in terms of a whole lot of variables, some of which are obviously very pertinent to the experiments. They measured the distances in terms of the momentum thicknesses, and I think they were looking at about times 300 downstream. So it was quite far. So yeah, so I think, look, in that case, we were only able to look at the far wake. And there, I mean, it was interesting. They looked at a whole lot of different generators, different shapes, everything. But as long as you go further enough downstream, they all tended to the same shape profile.
Yeah.
All right. Has that answered your question? Cool. Yes. He's happy. How are we going in the audience? Anyone else feel up to asking a question? I do have a quick question, if I can jump in again, sorry.
Sure.
So I'm not sure if you'll be able to answer this because you're kind of more on the deriving kind of side of things rather than the numerical simulations themselves. But did you get a feeling for kind of if you changed, say, the grid resolution in any of the simulations, did you have a feeling for if like particular models would work better in that case or not? Or did you just kind of have one grid setup?
So I think this is one of the cases where I wish, you know, my collaborator was online.
I totally get it, yeah.
Look, I'll tell you there were some very interesting features of the numerics. So with the extended model, the same kind of scheme was used because all the other models are subcases of that one. And then some of them do have exact results. So we could compare it to that. And I mean, largely the error was tiny. It was like 10 to the minus 7.
Mm-hmm.
But when some of the parameter values were varied, particularly the 1K2, as you got greater than a value of 0.5, the numerics actually seems to start to break down. So that was one of the interesting things. And there were a number of things that were tried, looking at grid sizes and all of that. But we were working with such a high resolution already that it didn't really appear to resolve the problem. And of course, that could be an interesting consideration. Maybe there's some physics involved. But as you know, with experiments and simulations, I unfortunately don't know too much.
Thank you for your answer.
Yeah.
Thank you for your answer. All right. Any last minute questions? Yes.
Hi. Yeah, I'm not familiar with your field, but I'm just curious about there are two constant variables you tune. It's the K1 and K2. I'm just thinking, what's the criteria to tune that constant? Yeah.
Thank you for that question. So basically what we looked at, so I perhaps should have, if I had more time, I should have explained that. So how we actually got those constants, so I should probably say it didn't end up being the K1 and K2. We rescaled in a particular way so that we could compare all the models, which I didn't have time to go into. So it ended up being a beta in a K2, but that's really besides the point. If you look at the sizes of the parameters, the beta is meant to be quite small. In fact, beta is 0 when you neglect the kinematic viscosity. So we first looked at a fixed K2, or just say K20, and we varied the beta. We noticed that the width of the wake did increase, but not to a very significant amount. So we did play around with the parameters, but without having a little bit more knowledge of all the full-on set of experimental data, it did become quite tricky. And these are quantities that can be measured through the use of comparing to data. So I must be honest, I don't think we used the most sophisticated techniques, but we did look at the effects of those values, which we felt was significant enough to at least say that we think that this model fits the data better than all the others.
Yeah, okay, thanks.
Thank you.
So I have a question in the chat. Geordie, would you like to unmute and ask it? Or I can just read it.
Oh, can you hear me? Hello?
Yes, we can hear
you.
Good. Does the mixing length compare with the turbulent correlation length or integral correlation length in the way that it varies along and across the wake?
Sorry, would you mind just repeating that?
Prandtl's mixing length, the value that it ends up getting from the fit, how does that compare with the turbulent correlation length, the integral correlation length?
So I can tell you that, thank you for the question. I do not have an answer for that. But what I will do is I will make sure that I get an answer for that. Okay, so turbulence correlation length. Thank you for that. I will look into it. I appreciate the question, and any input is extremely helpful.
Okay, thanks. I don't know the answer either.
All right. Anyone else from the audience? Otherwise, it's kind of getting near to 5 p.m. here, so I think we might finish up. Thank you again, Ashleigh, for an excellent talk.
Thank you so much again.
Oh, yeah, it was fantastic to have you. And I'll hopefully see everyone else next week.
Thank you.
Thank you. Have a wonderful evening, everyone, or morning, wherever you are. Thanks again.
Thank you.
Cheers.
See you.
Yeah, have a good rest of the day.
Thank you.